rewards that they may lead to. So they took that algorithm, the AlphaGo people did, and as Silver mentioned in the video, they used 2 neural networks to actually make that Monte Carlo tree search more efficient. Okay, and in doing so, they were able to play Go in a way that no one else has been able to do it before. So currently, the state of the art, all of the state-of-the-art Go systems use Monte Carlo tree search, but the current approaches are just too limited in either how deeply they can go into the search tree or how broadly they can go in the search tree. And as a consequence of that, they have, you know, their understanding of the value of actions is going to be just not as good as what they've been able to achieve with. So I think that's one of the big innovations, is that they took Monte Carlo tree search. They actually used 4 neural networks so totally they had 4 neural networks. Once they started playing, they were using 2. And so the integration of these neural networks, once they had them trained, which was pretty impressive, using that with Monte Carlo tree search is what let them play Go at this level.
So the AlphaGo can't learn as it's playing the game. It already has a static set of.
So I don't know. I looked in the paper and tried to figure that out.
Yeah.
It wasn't clear to me. It wasn't clear to me exactly what was happening during play. And because in principle, you can do this Monte Carlo tree search and get a tree and, you know the value of each state and know what action you should take out of that state. So in principle, you could do that. But it wasn't clear if they were running approximations while it was playing, or if they had done all the calculations offline and then they just played the game.
Well, so yeah, I don't know, so they're doing the rollout during the game, right? So
they are
with a fast rollout, right? So they decide, okay, in this given state, now I have current set of action I could take, and then I have a distribution. Okay, which ones are going to be more likely to work than others, and then it just samples from that, like 100 or 200 or so, right? And then explores the tree down. So they have these. You mentioned the 4 neural networks, and so one is this, and again, it's like the Atari paper, right? They have this deep neural network to try to predict the value of state given the input, and that's the normal, like 13-layer Google Net kind of thing. And then they have, but it takes a while to evaluate because you have such a deep network, and so they have this fast, like just 2-layer version of it that they can use then to quickly suggest a lot of possible moves that they can then explore. So they use the fancy one, the 13 layers. To in a funky way for these bonuses to kind of preload the nodes and say, okay, here these are going to be good states, and then during the game, then they're in a certain state, and now they just sample and say, okay, these are probably good actions, and I'm going to explore those and see if they're going to work out.
Okay. Just to go back to reinforcement learning and creativity, as you remarked, those are separate things in your mind. So the core issue is, with supervised learning, you require a teacher to tell you which examples correspond to a positive example, or a binary label, either 0 or positive or negative, as you were remarking earlier. So in that way, you could think of, okay, well, AlphaGo is only going to be able to perform in a way that's dependent on its past history or its prior knowledge. So when Seedol, or like when like against the match with Fang Li, or also against the match in 1996 in chess with Kasparov, he tried an unusual opening move, right? Because perhaps that wasn't in his database. So is that a wrong way to think about, like, is AlphaGo still capable of some set of creativity by combinatorially commuting across the things it's learned from? Or is creativity still something that's not attainable in the same way that we would think of when we're thinking of human creativity?
Well, I mean, to me, creativity is I mean, here, what they're doing, I mean, you have a game like the complete information, right? You have your rules, right? You know what what you can do, what you can't do, right? You know what the board is, and so and then the power from AlphaGo comes from, well, okay, you train it to be good at assessing the value of a certain position, a certain move in that position, and then you can explore quickly a few more. I mean, it's sort of like, I mean, it's a little bit smarter in that way than Deep Blue, right? Deep Blue did the chess program, right? Did like 200 million moves per second, and so that was just brute force. And now it's a little smarter in that it's better at evaluating, okay, which situations or which moves are good moves, and then I'm going to try to run with those. But it's not. So I have this quote. I mean, so Edison says genius is 1% inspiration, 99% perspiration, right? And so AlphaGo is great at the perspiration part, right? And the same way as Deep Blue, right? I mean, they're great at doing 200 million moves and whatnot, right? So a lot of perspiration there, but then they're still at that 1%, right? And so I think that's something that there's just no inspiration in that respect, right? I mean, so like one test of creativity is this one where you have these like 3x3 dots, right? And you say you connect them with 4 lines, right? People know that one, right? So you have 3 dots and you have to connect with 4 lines. And the only way you can do this by having the lines go outside your grid, right? You go like this, like that, and like that, I think, right? And so if you don't put that in, the computer isn't going to get that, right? I mean, it's going to explore all the states, but so basically, I mean, if you have a well-defined objective function, and then you can play a lot of games, but human intelligence is a lot, and creativity is a lot more than that, right? I mean, it works well in this one-of-a-kind situations, right? Not like, okay, I can play a million games, but rather here in the situation that I'm not trained on, what am I going to do, right? And but there's no clear objective function, right? So I mean, life I can't play to the end, right? And I'm gonna wind back and do it a million times, right? So I mean, I think it shows that Go like chess, right? I mean, it wasn't like people said, I mean, maybe 5 years, 10 years, but there was no doubt that at some point computers are going to get there because I mean it's a combinatorial issue, right? And so, but I mean that's not intelligence, right? It's not So, and that's also what they say at the end of the paper, right? Okay, well, it's a little bit better in that it has to evaluate fewer moves, but then, I mean, humans, I mean, it's sort of like planes fly, right, and birds fly, and they do it differently. And so I mean, if you just look at Go, right, they both can play Go well, but humans don't evaluate thousands of moves, right? And so they're a lot better in terms of the learning part, right? That they can learn from these examples without having to play a million games, right? That you somehow develop strategies, right? That you don't have to do these fast rollouts because you don't know, okay, which one's going to work. Right? So I think there's still very different fundamental differences, right? It's not, so rather what this shows us is that Go isn't a great problem to look or to understand human intelligence, right? Because it's not, it's a combinatorial issue, right? But so rather we need different kind of tasks, right? That then help us better understand, okay, what makes human intelligence intelligent, right? And creativity is interesting because it's, but I mean, that's something in neuroscience and counter neuroscience, people are, I mean, that's basically what we're trying to figure out. I mean, what is creativity, what is intelligence? And I mean, the reason why I mean, originally I started out, when we study AI, right? But the thing is, we don't even understand real intelligence, and then doing artificial intelligence is, it gets a little tricky, right? So, and so understanding then how the brain does it, and then saying, okay, here we have some ideas for algorithms that we can now teach computers, right? And that's been very fruitful for different domains, like we work in vision, right? So recognizing objects is now basically, these algorithms work in a very similar way to how the brain is doing it, and now they're taking it and then just using the fact that computers can do it a lot faster. But if you go to these higher level aspects like creativity and intelligence, I mean, there we really, I mean, that's, I mean, the brain is still so good at these things, and we need to get a handle on that, and that's what makes neuroscience so exciting. Because, but yeah, I don't see this as intelligence, but rather, yeah, it's a smart way of learning, and then crunch, right? And then,
Mark, did you have a comment on?
Yeah, I'm not going to dabble in creativity because that's Max's expertise. But I mean, I think one of the amazing things about the sophisticated learning algorithms that we have is their ability to generalize. Okay? And I don't think that we should confuse that with things like creativity. So for example, if you know the Google self-driving car and the DARPA Grand Challenge, they set this robotic car off on a route in the desert. It had never driven that route. It encountered obstacles that it had never seen before. It avoided the obstacles. So, you know, I think in the old days of artificial intelligence, when people achieve things like playing checkers or playing chess or things like that, people could say, well, I mean, you know, it was just part of its programming, you did this, and I think there's a little bit of that with the AlphaGo system. But if you look at what, you know, some of the tasks that the self-driving car has been tested on, it's getting harder and harder to say that you programmed it to do that, because it actually had never been on that road before. It had never seen that rock before, and yet it sensed that it was an obstacle and avoided it. And in doing so, did not drive into the cliff on this side or drive off the cliff on that side. So computers are getting more capable, and they're able to generalize to situations they haven't encountered before. But I'm not sure that's the same thing as creativity or intentionality or some of these other tricky philosophical things that some people in artificial intelligence worry about.
So I guess, yeah, just going back to the difference with Monte Carlo versus combining it with neural networks, I can't really speak to it on the technical end, but just in terms of how it plays Go, you know, any I guess fairly good Go player, after the first 15 or 20 moves of the game with these pure Monte Carlo type programs, any Go player can tell you immediately that's Monte Carlo. You know, that there is no human being on the face of the earth that would ever play this move of any skill. And it still managed to win, in part, I think, because players were so freaked out by these unusual moves that it would play and make work. That was one of the reasons, I think, why it was good at beating amateurs. It was also a very good program. But you know, one of the things I found fascinating, Facebook actually, of course, had a competing program that hasn't yet reached the same level of strength at trying to beat Go, and they tested their program online with the general public. And I got to play their neural network program in one of its earlier stages, and it was weak enough that I beat it at the time. But what fascinated me about it then, and the same thing with AlphaGo, was it played far more human-like than any pure Monte Carlo program. I actually, being the nerd that I am, I actually did an informal little Turing test online. I posted a game that I played against AlphaGo, now against Facebook's Go playing program that used a neural network, and then I played another game that I played against a human being. And I posted both these games, and I posted on Facebook, had a poll, right? Who am I, and who's the computer? You know, who's the computer in these games? And had I done this with a Monte Carlo program, I could easily assure all of you, 90+% of the people would have immediately been able to spot that's the Monte Carlo program. With the neural network-based program, it was about 50-50. Only 50% of the people were able to tell that's a computer program. And I mean, there are still a few little things that AlphaGo does that you can clearly tell, oh, well, that's really because it's a computer that it does that. But it's really, really human-like, actually, to a surprising degree. On creativity, just in terms of its Go moves, there were a few points in the game where it played moves where it also played moves that no human would have probably considered, but not because these moves were just, I guess, you know, for lack of a better word, just out there moves. These are moves that once you looked into them deeply, they actually had a really deep foundation in what they were attempting to do. They were analyzed a lot after the game, and some of these moves, despite the fact that no human would have considered playing these moves, they turned out to be very effective moves as you went 15 moves deeper, 20 moves deeper. You just looked at this move and it just, you know, it almost starts like shining and how effective it was on the board, despite the fact that no human being would think that this was a move that we should play. So just my thoughts.
Thanks for the thoughts. So we would like to open up, we've gone through all the main issues that we would like to talk about. We'd like to open it up for questions from the audience, and then we'll be having a reception after this with lunch.
Do you think there are benefits to having a machine that will make a mistake? I mean, I know Mark said that you can theoretically have a perfect game, but if you want to try to model kind of this creativity, or as I understand from talking to people, I don't play Go, but it's very about intuition and things like that. So the fact that it made a mistake, is that because it's trying to use this intuition, and maybe an error kind of points to its humanness a little bit?
Well,
you want it to go and try to find things that maybe.
I guess treating AlphaGo as a human being for a second, if AlphaGo were a human and I were saying, well, why did I think it made this particular mistake? I guess it was first off, it was a really unique situation on the Go board. You had a bunch of smaller fights that were slowly starting to connect together into the center. So playing one move affected at least 3 or 4 different areas that were sort of close by. It also involved a concept called co, which is a little bit hard to explain, but basically revolves around the rule that the board can't copy exactly any board position that was previously on the board. And while that sounds like a pretty simple rule, it can lead to a lot of complications in a game. And computers traditionally haven't been very good at dealing with co. AlphaGo is certainly better than computers before it, but it's still, apparently, this involved a co, and then it also involved multiple smaller fights combining together into one. So I guess I would just say maybe it was too obscure of a variation for, I don't know, maybe you can tell me more about the neural network side of things.
Well, I wouldn't want you to make a mistake, right? I mean, if it's doing my orthopaedic hip surgery, for instance, right?
That's very small space.
Are
you moderating?
Yeah, no, I thought you had something else to say. Would you like to?
Yes. Thank you. Fascinating discussion. I have a lot of questions, but I'll ask only 2. So my first one, if I understand it correctly, AlphaGo can do only what is programmed to do, right? It's not doesn't go beyond that. And surprising or creative move is for us, right? It's because maybe we as humans haven't thought about it, but it was programmed to move that way, right? So sort of the concept of creativity or mistake don't really apply.
Well, it's still new for the program too, because it couldn't have explored all the states, right? So you basically are in a given board, and now it's doing the rollout and says, okay, in this given state, I'm going to pick a few that look good, and then it's gonna, and it might never have done those before, right? And then it goes down that tree to a point where it says, okay, here, time's up. I'm gonna have to evaluate the board and then pick the best one. So if you say, yeah, if there's your homunculus in it, says, oh, I've never seen this before, right? but yeah, so I mean that's what makes Go so hard, right? I mean that you can't explore all the possible states in advance, and so the program might also then be in states that hasn't been before. It just has to go with I mean that's where the Monte Carlo stuff comes in, right? That it tries to then pick, okay, these might work out, and I'm just going to go with those instead of all the possible moves.
Ellie?
I think my question is pretty similar to Jeff's, but what is the advantage of having it designed to win by 1.5 and not just maximizing the possible number?
So basically, if as I understand it, on the level of Go, if it has 2 choices, and one choice it projects a 90% chance to win by 1.5 points, and then the other is say an 80% chance for it to win by 30 points, it will choose the 1.5 point win. So I mean, basically, I guess if it's the same probability, it probably won't matter as much, but it's a lot harder to win by more than win by less. So usually it aims towards this 1.5 point win, whether it's
what if there's a spread?
A spread by
Just saying that, yeah, there's a covered spread.
So just, but in theory, you can also win with less than 1.5.
Yeah, you can win by 0.5, but this goes back. Yeah, you can win by half a point. But half point wins are, how do I put it? It's a little hard to explain. They're sometimes it's very easy to make a half point mistake. Very, very easy to make a half point mistake. And even with a very good neural network, and so I think they did that. They boosted it to 1.5 on purpose, because even if they could have done it by half a point, I think the fact that it might make a half point mistake somewhere and flip a win to a loss made them decide to make it 1.5 points. So that's just my opinion. I don't know that for a fact.
Actually, there was a human analog to this. Michael Redmond is the strongest American Go player of all time. So he said when you're counting, you want to be like 5 or 6 points ahead, because if it's less than that, oftentimes a funny thing happens in the end game.
Make a mistake, wholly disappears. AlphaGo is extraordinary at its end game at calculating those tiny little quarters of a point, eighths of a point that one move has different from another. It's extraordinary at that.
Scott?
I guess my question is inspired by Max, but I guess anybody can handle this. Is the idea of as a neuroscientist, I feel like I want to have something that so you say it's inevitable that the chess game within 5 years or the Go game within 5 years. I want to know, do you feel like there is an inevitability, or even that anybody who cares to do this, that someone will be playing like the top champion, not just beating the top champion behaviorally, but playing like they play and doing the same things they do, maybe even making the same mistakes they make? Or is it the case like with the airplane where, we stopped at the airplane and that's what it looks like when things scale to fly that big, and we're never going to be waiting in security to get on something that looks like a giant falcon or something. So
Millennium Falcon.
So I mean, I guess that's something that I care about because it helps us understand the brain. It's also something that we can interface more, actually interface with, instead of saying, okay, well, this looks like it's driving to like a person, so that's good enough for me. But if I'm going to stick it in my brain or something like that as a sort of a brain-machine interface, or if I'm going to use it to understand how I drive, that's not good enough for me. But it seems, do you think there's other people out there who think it's not good enough? I guess is the question.
Well, it's actually interesting because what they write in the paper is, so they trained the Google's deep network to predict, so they trained a lot of the human moves, right? So given a certain state, what's the best action that the humans would take? And then, so they predicted like 57% or so, right? But then they actually have to take that and use it as a component, because the goal is not to emulate humans, but to win the game, right? And so they actually have a different objective function, right? So the deep net was trained, the backprop net is trained to emulate humans, but that's just part of winning the game, right? And so you can say, okay, if my goal is to be human-like, right, I wouldn't optimize to win the game, but I would optimize more toward, okay, well, let's play like the humans do. But here again, the objective is I want to win the game, and then at some point you might then make different moves because you have more the ability to go into depth, right? And I mean, in the end, like theoretically, you could predict, okay, at this point, the perfect strategy, right? And humans don't have that, right? We do work differently, and so I think at some point then there would be differences. But here they explicitly say, okay, we had to now change from this to that objective function.
And at least in artificial intelligence, people break down into different philosophical stances, right? I mean, there are people who would look at this and think that it's just an engineering accomplishment and that it doesn't say anything about artificial intelligence, and they would actually want it to solve problems more like we think we understand how humans solve problems. But in AI, I mean, you get people who break down into different philosophical stances.
Any other questions? Yes?
So we said that AlphaGo responded really well to like moves that it hasn't seen before, like unusual moves that it hasn't played. But in the fourth game, what do you think was so special about that, like what they call the divine move of Seedol, that made AlphaGo make a mistake, or if that was a mistake?
Well, so actually it's interesting. A lot of professionals did a very, very deep analysis after the game, and they actually found that there was actually a counter move which stopped Seedol's move. So it wasn't really a divine move, because there was a counter move that AlphaGo, had it played it, would have stopped his move. AlphaGo didn't find this move and made a mistake. I don't know for sure why it missed this. I think it was a very, very unique kind of board situation. And it was a very, very, I guess, very difficult to see kind of variation. I mean, I would not expect that someone besides a strong professional player would have been able to properly find this counter move. So it required, I guess, a lot of intuition is what I would say. I don't know the specific reason why it missed this move though. Do you guys have any insights on why it might have missed it?
Probably lost the Wi-Fi connection.
I mean, it just doesn't have perfect knowledge,
Right?
And so, if you could know how to exploit that, I suspect that it wouldn't be as successful. But clearly, it's the knowledge it has was good enough to beat someone who's very good.
Mm-hmm.
So would that be an instance in which it would be preferable to be playing like a person? I mean, like, is that a mistake a person would?
Well, I think hindsight is always 20/20.
Right.
Do you have a question?
Yeah. Well, just to that last discussion, it was a really bizarre looking move. Like, I can't remember, but it's like a placement inside of two stones.
Yep.
And I saw after the game that that they went back and looked at the record and said that the policy network said there was a 1 in 10,000 chance that
Yep.
Seedol would play that move, and so didn't read it very far because it was
No one would,
bizarre
it's a
looking.
very unusual move. It's almost, that kind of move that he played would almost never be a good move. But in this very, very, very particular situation, it just happened to be. So yeah.
Yeah, and I had, one thing I was wondering is how much, so they took a lot of games with expert players and then ran it through the network. How much data would be necessary to write, to create a computer that could do this? I mean, obviously there's enough
To do what?
to play Go well, so there's enough. I'm trying to think about this more abstractly, right? So like they're talking about how we might be able to apply some of these techniques to medicine.
Yeah.
Right. So I guess I'm wondering how much data do you need to master any particular game?
10,000 hours.
I mean, it depends on the complexity of the problem, right? And I'm actually glad that you brought that up. I mean, I don't think Google bought this company because they have a good Go player, okay? And I think that, and let me just tell you, I mean, I think it's a fantastic accomplishment. But also keep in mind that Go is an example of a huge class of really important problems where you're taking a series of actions and you get some reward, or you're in this alternating game with an adversary, and then you're trying to maximize your reward. And you know, there's a huge number of problems that fit into that framework. And the other thing, customer service and medicine, right? I mean, so, and I also want everyone to keep in mind too that, you know, this it was a great accomplishment, no doubt about it. And there's been a lot of excitement about it. But keep in mind that research on this has been going on for 60 years, okay? And in 1950, Claude Shannon wrote a program that learned how to play chess using a lot of this, I mean, very similar ideas. And there has been a progression in the research ever since. And you know, these guys weren't even the first people to apply convolutional neural networks to the problem of Go or use Monte Carlo tree search. So they did some really innovative things, but keep in mind that a lot of people have been working on this for decades. And it's a great high watermark. But it really is how research works in the scientific community is, you know, everyone is making these contributions, and then, you know, there's this big thing that happens and people are very excited about it.
Yeah, I remember in certain of the games, the commentators mentioned that AlphaGo would play moves that looked to us like mistakes, but that on further reflection seemed to be effective in getting to that goal of winning by 1.5 points. And I remember the question was raised how that would work in scenarios like medicine, where you basically be trusting a machine, even though it was doing what seemed to be unorthodox or a mistake, and then you're trusting that it somehow is the best way to get to this desired end. And I'm just, you guys have comments on that? That's a great question.
Yeah. Well, I think that's one of the challenges in medicine that have kind of stymied things a bit. But I think so for instance, radiology is one of these areas now where you can have a computer do a triage, right, and then you can still have a human expert look at it to verify it, right? So you can. So we had a DARPA project where the idea was, it's called Luke's binoculars, where you survey a wide terrain and you chop it up, you show it to people really fast and pick up their brain activity with the EEG to predict is that interesting or not. And so what you had there is initially a staged computer vision system that had a high rate, was very good at throwing out what wasn't interesting, and wasn't too good. So it still made mistakes, but you have the mistakes so that rather there's some sense of inclusion, right? So it gave you a rock sometimes that was not very interesting, right? But it didn't miss a person, right? And so same way here, you can imagine that you have the system then trained on where you have a high hit rate with maybe also a somewhat high false alarm rate, but you can still triage a lot of stuff, right? And then focus on those. But it's hard. You're not going to have people at least at this stage, maybe depending on how much you want to pay for healthcare, right? Then, so it might still be better than nothing, right? I mean, you might see if you don't have healthcare, right? You type in your symptoms, and when you get something out, it's better than nothing, right? So it's a decision that people can make, but it's I mean, that's one of the concerns, and actually there are then AI techniques, I mean, that you then have the system justify, which is easier in like expert systems where you have like facts, you can say, I think this because of that, right? It's harder with these deep neural networks because, I mean, then you just have these weights, they have these very non-local representations, and so it's much harder to justify, okay, why am I making this decision? But even there are ways to then justify, okay, why is this coming up? But this is indeed one of the concerns there, that, but there are ways and people are, you can still have the computer help out and not make the final decision, and then have still have a human in the loop.
And you know, doctors make mistakes too.
Yes.
You mentioned that AlphaGo thinking or thinking process is different from our brain, right? It's developed differently, and but if I understand correctly, AlphaGo is good only at playing AlphaGo. Not other, it's not transferable to other areas or anything. So my question, as we as humanity develop this artificial intelligence, are we creating only AI in these silos that cannot either communicate or do different things? And what is the trajectory that people who work on artificial intelligence are trying to do? Because when I see it's very separated in different silos, and how useful it's going to be for us if we develop it in that way.
Well, it's getting better and better, right? So the first one was you had the deep networks just applied to like object recognition, right? You had an object, then you had to recognize it, right? And now you combine it with reinforcement learning, you can develop strategies, right? And so I think those are good stepping stones. Then, and now we're going to get a handle on, okay, well, now, so here we still have clear objective function, right? And then, I mean, the next step is then, okay, well, what if you relax that, right? I mean, so there's this progression there that you get to more and more challenging computational problems, and so I think it's actually, I mean, now we are at this point where, okay, what's the next thing? Right? So we have deep networks, we have reinforcement learning. So what's the next thing we want to put in there to tackle a bigger range of problems?
Yeah, I think you're right, and you know what you're saying has probably been the most persistent criticism of AI systems since the very beginning, right? You produced a system that did this, it can only do this, and so you know, I agree with that. You know, one thing I would say about AlphaGo is, you know, again, you know, they solved an example of a class of problems. So now we have a way of solving this entire class of problems where you're doing reinforcement learning, you have rewards, and we can do that on problems that are larger than anything we've been able to do before, okay? And I think that computers are getting more and more sophisticated. The algorithms that we're developing are more and more sophisticated, that you are going to be able to identify a broadening of the tasks. So again, you know, going back to the self-driving car, and you know, I remember reading self-driving car papers when I was in graduate school in the mid-90s, and now we've got a car that drives blind people to the Taco Bell, right? So, you know, operating in an urban environment and avoiding, you know, people with baby carriages and people cutting out, that's a very complex environment. And yeah, it's a task, self-driving task, but it's very different than chess or Go or anything else. You know, I think in the next 50 years, you're going to keep seeing, it'll be incremental progress, and there will be big, exciting things that happen, but you're going to see these AI systems doing more, you know, more and more complicated tasks in more and more complicated environments.
Yes.
This is perhaps for the neuroscientist on the panel. So we have this problem where this AI is being developed in can only do certain things. What disciplines within neuroscience perhaps are providing hints to the AI community about how to maybe go forward and create an AI machine that can do lots of things?
Well, I think one thing that we're interested in is, for instance, what the human brain is very good at is reusing and building on what you've learned before. And so, so our brain is very hierarchical, right? So it breaks down a problem, complex problem into a lot of little pieces, and that helps you deal with a messy biological hardware. And so you do like simple things over and over, and you can do very complicated things. But an advantage of that is that you now have things at all these different levels that can be reused for other things. Right? And so we still don't understand how the brain is doing that, and that's something that we understand better how the brain is doing it. But I mean, that's really so right now, as mentioned before, right? You train these systems on very specialized problems, right? And what you've learned on one doesn't necessarily transfer so well to another one. Right? But yet we are very good at that. And so I think that's something where it would be helpful to learn. I mean, so when we look at learning, for instance, these deep neural networks, what they usually need like 1 million examples or so to do something useful, right? Yet, I mean, you can show a toddler a picture of a dog and a cat, and then they can pick out, like I showed them other pictures, and they can pick them out 80% correctors, right? And so we're great at. So we're n as you know, if examples goes to infinity, right? Computers are awesome, right? But humans are great at when n goes to 1. Right, and so understanding, well, how can we learn so well, right? And probably it's because we can reuse stuff that we says. I mean, it's an example that we work in the lab, right? I mean, instead of, for instance, if you have to learn to recognize donuts, for instance, right? I mean, it's not one of the problems we're working on, but it's very, very important to have survival. So then you can say, well, this is like a tire, right? And then you could use that information, and then it actually shows that you can actually learn things faster that way if you say, okay, well, it looks like X, Y, or Z. And so understanding how the brain does that, I think is going to be very interesting then for these AI applications to reduce the learning problem and also then help make it easier to branch out to new tasks.
Thank you. Lavon?
So kind of expanding on what you just answered, would you say that when looking at humans, we're a product of evolution, right? Which are, yeah. I am a product of evolution. So could you say that their n is truly going to infinity? So the way evolution sometimes, well, it works is you get born preloaded with certain cognitive architecture that's preset to survive in this world. So you've been trained over, hundreds of thousands of years to be effective at manipulating these things and, not crashing into things and social interaction and whatnot. So do you think that is a good analogy in terms of, yet computers will still have to learn a lot in order to get to our level? Or do you think there's more fundamental difference, like neurons are computational units, but they do computation in totally different ways that we don't understand, and we have to understand that in order to,
Yeah, I don't think you have to make the evolution argument because, like, for instance, if you think about writing, for instance, and reading, right? So that's something you're not born with, right? And that's something that's so recent culturally that evolution couldn't have done, right? And and that's something, I mean, of course, the debate Chomsky and that, like, I mean, there's something special about the human brain, right, that allows it, that's optimized for language, right? And so if we, I mean, that's why now this is in the connectome, right? I mean, how do all these things fit together, right? And so how is our brain optimized for cognition, right? And to do it in a way that's a lot better than what we know from animals, like monkeys. So there's something about the architecture, computational architecture of our brain, right, that makes it very good at cognition, right? Which is why we rule the world and not the apes, right? So which is very good, right? And yeah, I mean that's precisely goes back to this question: I mean, what is intelligence, right? And part of it is in the way that the brain works and how things are wired up, but we don't really understand it yet, right? And that's why, I mean, again, one of the reasons why neuroscience is such an exciting point right now, because we have the technology to look into, okay, well, how is the brain actually doing these things?
Do you think the architecture of our brain will change as we continue to rely on artificial intelligence that is better than us? For example, I use Google Maps to get here. I didn't have to think where to go or so. I just was following. So then this part of my brain, I guess, is not
Hippocampus
developing.
shrivels up and
Yes.
dies.
And as it continues, whether we'll become weaker at survival and so on. What, is there any studies along those ways?
I want to
If it
add that.
affects your ability to reproduce, then it will.
I want to add that we need to become very good at navigating inside the phone, so your hippocampus still works.
Well, I think it's right. They did this paper in Nature a couple of years ago where they looked at how that actually the ability to use Google affects the way we think and solve problems, right? That we don't store as many facts. So it's like, here I can get this stuff, right? And so I don't think it's evolution, right? I mean, it's not like within a generation or within 10 years our brains change, right? But I think it's just this architecture is so flexible, right? That it can deal with. And that's why augmented cognition is so interesting, right? That we can find ways, like it was said before, right? If we can find ways for computers and brains to optimally interact, right? I mean, then you can get the best of both worlds. And so, I mean, because there are things computers are better, right? I mean, they have perfect memory, right? You can, and they can be building things per second, right? And so now the challenge is then to see, well, how can we connect it? At what level do we have good interfaces, right? And so, and yeah, so it's exciting times because, again, we understand the brain better to see what's the best way of interfacing the two. And then I mean, DARPA already has a project, the RAM project, right, of storing active memory, where the idea is, okay, we have some idea, I mean, the hippocampus is very stereotyped, right? Can we have a little implant to then restore lost functionality? And that's, I mean, it's really cool stuff, and you need to understand how the brain is doing it, right? And the side effect then might be, okay, well, then we can also go completely silicon, right? So we had a project where the idea was that so we have a model of how the human visual system works and recognize objects, and then what you can do then is to basically put in your thinking cap, you look at images really, really fast, like thousands of them, you can do a lot of them per second, right? And you train a little mini-me of yourself on the computer, right? And the computer can go on to look at images and classify them the way you would, right? So, I mean, it's just a really exciting time. But we still haven't scratched the surface on what makes the brain so cool at learning these tasks. And I think AlphaGo shows us like the differences. I mean, you can get very good at with these brute force approaches that are then smarted up a bit, but still, I mean, humans. I mean, maybe I don't know. Josh can talk to that about like, do you play through different moves, right, or you just know that there is a good move, right? And so yeah, there's a lot to understand yet, and it'll be interesting to see how the brain does that.
That's the question I was going to ask, which is the computer has a position it's never seen before. The first step is to come up with a list of plausible moves that it's going to look at, and the way how does it get that? One is Monte Carlo. That seems very inefficient, and it could look through a million games that have been played in the past, but they're all different from the current position. So you need some way to get from those games to get insights to the current game. I just don't understand how that happens in AlphaGo.
I think it's through the neural networks. And so we didn't get down into the weeds, but and Max can talk about, you know, these deep learning networks. But one of the things that they did is they represented a board position using 48 layers. So you can think of the input to these networks was 48 layers, one of which was, you know, the positions of all the white pieces. The next one was the positions of all the black pieces. And then they had 40 some odd other layers with information about the board state. And I'm not 100% sure how they wired up the deep convolutional neural network, but based on that information, it was able to generalize the things that it hadn't seen before, and that was what was guiding. And so to me, it was kind of interesting because, you know, the neural networks really were doing something kind of neuroscience-y. And then they were using this rather traditional AI search technique, but the neural networks were kind of driving it. And that's how they were able to achieve something that could, you know, explore and make moves in a short period of time.
So one thing that got mentioned a while back is that AlphaGo had two different networks for doing like board state valuation. One was like 30 levels deep, I think, and was therefore kind of slow, and one was 2 levels deep and very fast. And so then they were used in tandem to do sort of move selection and pruning. And so to what extent does that match or sort of model the human neural architecture, or even the human like sort of more conscious approach to Go, or is this computers just like, is this computers moving towards human like thinking and structures of thought, or is it computers going in a totally different direction?
Well, I guess just how I think about Go moves when I'm looking at a Go board in a given situation. First of all, obviously you look at your opponent's move, and then I guess it's a mix of experience and intuition about where to start looking, because of course there's hundreds of moves on the board, and based on past experience and what looks like it could lead to favorable positions in the future, that will give you anywhere between 5 and 10 possibilities, and then from there it's a matter of looking maybe a few moves deep into each of these possibilities, and then pruning from there. Oh, well, 2 or 3 of these moves, if I go a few moves deep, they look really interesting. And then from there, I can, with those fewer moves, I can go even deeper. And then at the end of that, the one that I think is the best one is the move I end up playing. So I don't know how these two policy networks
Well, I think so. If you look at the performance of the deep network, it was like 57% correct, right? So it was able to predict what a human expert would do in 57% of the cases, right? And so that actually had a huge impact on, They showed this figure that small improvements there really had a big impact on the score, and I think that's the biggest difference with humans, right? I mean, presumably the human expert would be 100% correct, right? Or predicting the human expert move, right? So, and that then reduces how much you have to simulate in your rollout, right? With a fast policy, right? I mean, if you always make the perfect move, you don't have to simulate. It's the perfect one, right? And so I think here the fact that your total layer network was only able to do 57%, right? And then you add 99% perspiration, right? And just say, okay, I'm gonna try all these moves, right? And then see which one's gonna work out best. I'm just gonna go with that. But on the human side, right, we're just better at that initial move, and then you get away with, okay, let's just try 3 moves or so. And so I think if they optimize that first part, right? I mean, that is probably one of the biggest gains that could be had, right? You saw like a few percentage points there, can get you like 100 points in your rating.
Sure.
Paul Kanan from mathematics. There's one issue that hasn't been raised here, and that is homogeneity versus heterogeneity. Humans are very different. There isn't a human brain. There are many different kinds. And the skills that a person has in a job, for example, analog skills, printmaking, as used to be used in maps, got superseded when we put in digital cartography, and now you're choosing from a menu. So I wonder about the issue of AI as a homogeneous norming force in society, and how can we ensure that the heterogeneity of humans is somehow protected by our AIs?
Well, I think that's what academia and arts are the refuge for the oddballs, right? So I think, I mean, they're just some the things that you automate, right? It's like, I mean, the map, you want to be correct, right? So I mean, yeah, like medieval maps, you have beautiful dragons in the sea, right? But for most of us, if you want to get to Walmart, right, then it's enough to have the right road, right? And so I think
but showing that is not so easy. The issues of generalizing, having a road and a river that you can distinguish, it's a difficult problem.
Right. So I'm saying, I mean, there's some. I think there's some way, some areas where heterogeneity is important, right? And there are others where you can benefit from computers being able to achieve, right, and individually, right? I mean, if I have the GPS that tells me here you over here, this is where you have to go. I probably take that over a beautiful map, right? That I don't know where I am, right? And so I think. But I mean, that's one of the big concerns, right? I mean, what percentage of jobs is going to be able to be automated, right? And so the percentage actually gets higher and higher, right? I mean, even like radiology is one example, right? I mean, it's not just the blue collar, but also white collar jobs. And so it's an interesting discussion then. What are we going to do? Are we all going to be dog walk? Well, dog walking probably also going to be automated, right? So are we all going to? So I mean, those are interesting discussions, right? But I think with AI, I mean, again, there's actually a lot more variability in AI because you can train the network in all kinds of different ways, right? And they, I mean, you have these local minima and whatnot, right? But it's again limited. I mean, it's not creative like we've talked about, right? If you have an artist, right, he says, okay, well, I'm going to draw it this way. You're probably not going to get that in the program unless you put it in. But then the question is, okay, what's your objective, right? And so for the GPS, I want to go from A to B, and probably don't need this.
Yeah, you know, in AI, there's the dystopian vision, but there's also the utopian vision where, you know, if we had these robots that were doing all these menial tasks for us, maybe we would spend more time doing Japanese calligraphy or something like that, right? So, I mean, I don't know if that would be the case because, you know, we're all working too much doing other things, but, you know, maybe if they took the drudgery out of our lives and we didn't have to grade exams or things like that, we would have more time to spend on the arts.
And walk the dead on.
Yeah, I think this is a great place to remind again that we'll have another meeting in about 2 weeks. There will be about an article that touches upon all these topics about how developments in AI can change how the society is organized and how resources are distributed and jobs are distributed, etc. Scott.
So one of the things Max recently said actually brought up another point that I was thinking about, like what Jeff asked, is it okay, is there a benefit to making mistakes? And the question is there a benefit to forgetting? You know, when you bring up the fact that DARPA has a project trying to improve the hippocampi of veterans, I would assume, or actually soldiers, restoring active memories. So it just, you know, when I think of soldiers and memory, I think of PTSD. You know, I think of that's one of the reasons, rightly or wrongly, but that's one of the reasons that, you know, we do forget is that if you have something traumatic happen to you, like I would be glad that this Go board doesn't, you know, if somebody in a baby carriage jumped out in front of it as it was a self-driving car, doesn't bring that into the Go game, and all of a sudden now it's like brooding over this and like, you know, and so there's a part of our emotional brain that, you know, that there's another intelligence, I guess, that's involved especially when we bring these things together, but even independently. I guess the question would be like, is there a way that we can, absent this huge, like, you know, the limbic system in this wonderful way that has its own flaws, have been able to deal with all these issues, you know, and not have PTSD and that sort of thing, forget things and you know, kind of fail on purpose, to incorporate that into these perfect silicon modules that we might have, especially with memory.
You know, I think they're interesting. I mean, so right now it's designed to replace people who have damage, right? And so I think there probably any kind of memory is going to be. I mean, it's sort of like blind people with a retinal prosthetic, right? So I mean, anything you get out of, even just a few pixels, right? It's just going to be great. And so yeah, but I think ultimately, I mean, as we move into augmented cognition, right? I mean, the question is like with also when you take these performance enhancing drugs or something, right? I mean, then the question is, okay, well, what do we want, right? And what are the dangers? And so I think it's, yeah, with anything that we got to be aware of, okay, what are the drawbacks, right? But here right now I mean, having a Go program, right, is of course the potential for misuse is somewhat limited, right?
Cheating Go
but yeah, I mean, then you have scenarios, right, where it's talking about like creditworthiness, right, or like even guilt or innocence, right? I mean, of course, those are decisions then that have to. So we have to be very aware of. Well, with great power comes great responsibility to say, well, how are we going to use this? But on the other hand, I mean, the reason why this is being developed because a lot of areas where people need help, right? I mean, like prosthetics, and I think that's like, I mean, this whole stuff about like brain-machine interfaces is driven by that. And yeah, I mean, if you're a gamer, you can use it then to do cool stuff.
Any other questions? Yes?
One thing I'm sort of having trouble visualizing, I guess, is when AlphaGo is learning, what exactly is it recording? Like, is it learning different intermediate states before Monte Carlo rollout, or is it hardwiring itself to be able to recognize? Like, I don't understand. You know what I'm saying?
So the first network that they produced was this thing they're calling the policy network. Okay, so they trained that on millions of games, and it produced a probability distribution over actions, right? And of course, I don't know, and out of each board position, there are tons of actions you could take. So it would just give you a probability distribution over actions. And that was 57%. So then, as Max mentioned, they used that to train up this other neural network called the policy network. And in terms of the architecture, they were identical, but what it did is it shifted the emphasis from predicting well for a given action to optimizing the actions so that you're going to win the game. Okay? And so that was one of the networks they used during play. And then there was a value network that they trained up. And for any board state that you gave it, it would tell you how many Happy Meals you're going to get from that position, right? Potentially. And then as Max mentioned, they had this very simple thing that they called the rollout network. And that would give you a very quick answer. Here's the board state. What is the action I should take out of here? And, they were able to get an action out of that in something like 2 microseconds. And that was one of the things that was one of the reasons that they were able to do these Monte Carlo rollouts so quickly. Okay, so the first network just kind of set up the other 3. Does that make sense?
Yeah, so when it's trying to figure out the probability distribution for the first network, right?
Yeah.
So it goes through a whole bunch of games of expert players.
Yeah, I think 30 million or something.
Yeah. Okay. And then from there, it's, I guess, what's it's storing in its data, right? Like, so in order to recognize that pattern, because there's so many different possible states, right? So how does it get from that to being able to generalize, I suppose?
Well, so the nice thing is, it's a deep neural network, and so basically you can go online, get Google's Tensor, and you can do it at home, right? So and so basically what they did is a very nice idea, right? They just take the Go board, 90 by 19 pixels, and take that as an image, right? And then voila, you can use the whole neural network. And so what it does is basically alternating layers of, so the convolutional part is where you just do the same thing over and over at different parts of the image, right? The idea being like it was developed for object detection, so face could be anywhere, right? So if I want to detect the face here, well, same thing there, right? To some approximation, right? And so the idea, then that also helps to deal now with unseen board configurations, right? Because I mean, you train it with one configuration, but then thanks to the convolutional property, right, you replicate this all over the board, right? So you have like local neighborhoods first. You start with small neighborhoods, then you replicate that all over the board. Then you put those together, you weigh them, and then now you have bigger neighborhoods, right? And again, you replicate that and over, right? So that's the hierarchical network. And so like for object recognition, the idea is that have simple features in the early stages, like edges, right? Here, edge, its own edges, right? And then I put those together to more complex, like corners or things like that, right? And then more complex to like face partish kind of things, right? And then faces, for instance, right? So the same way you can say, I have no idea about Go, obviously, but I mean, if there's a hierarchy there from local neighborhoods to bigger and bigger parts of the board, right? Then the way the deep neural network would approach it is start first looking at local neighborhoods, then bigger and bigger neighborhoods, right? And then replicating this all over, right? So that what it learns at some part of the board then also can be applied to different parts of the board, right? And so that way for free, you get, even if you train it on like 30 million human games, you get for free all the transposed versions of it. Right, so and that's that's one of the powers of the convolutional neural networks, right? That you don't have to be exposed at a face at every position, right? But just learning it at one position allows you to recognize it all over, right? And so the architecture that helps you with the generalization part, and then so you generalize, then you combine, and then you generalize again, so on and so forth, and basically you set all these connections then driven by the data, right? So you have an input. And then you have a move that would come out at the end, right? And then you want to adjust the weight so that when this input comes, it's going to say, make this move.
Thanks. Any other questions before we break for lunch?
Can't be done. Move on.
Who the guy who set up? So I apologize if maybe you already answered this question while I was setting up the lunch. But so taking it back to the intelligence research, the biological intelligence research, interfacing with the questions of creativity. One program that comes to my mind is like an old program that's called SharedBlue, I think. It was basically a program that was written to perform actions in an enclosed environment where you had cylinders and blocks and triangles, pyramids, and you could tell it to do anything to those figures, like take this and put it on top of that, put the square next to, put the cube next to the pyramid, and it would do it. So is it wrong to understand this world as a giant enclosed box that obeys certain physical laws, and we are computational machines that are born and programmed or evolved or created with abilities to manipulate it? So in that sense, we're not really general intelligence machines. If you give us some kind of a sensory input that we're not defined to understand, we're not going to understand it. We're not going to be able to solve it if we never encountered it in, well, scratch that last part. But so we are also limited in that sense. Do you think that is a correct analogy to make? And sooner or later, machines should be able to become just exactly like we are.
It depends on whether you're a materialist or a dualist, right?
Right.
Ooh.
If you think you're just an automaton that's wound up and is interacting in this world, yeah.
Well, at least for the tasks that we are thinking about, like driving cars and social interaction, not like, not necessarily like self-reflections or thinking about, I don't know.
We're thinking about free will, right? It's going to totally mess you up. So, I mean, like SharedBlue is fine, right? Because, yeah, you just tell it what to do, right? Oh, take that cylinder, right? But, yeah, I don't think we're like that.
I mean, for me, Max is going to be upset with me, but I mean, I don't really care, right? With artificial,
You just won the lunch, right?
I mean, there's an open bar, right? For me, artificial intelligence is, software is here to help people most of the time. Would it be helpful for the software to be able to reason and see and understand and learn? And the answer is yes. And so, we produce learning machines, and if the algorithm that we end up using is biologically plausible or inspired by biology or has absolutely nothing to do with biology whatsoever, I don't really care, right? I'm a computer scientist who's trying to solve problems along those lines, right? And there are certainly people in artificial intelligence who do care and want it to be biologically plausible, right? So for me, if the car takes the blind man to Taco Bell and helps him get his cleaning, and it's a Bayesian network, that's a win for me, right?
Well, we're Bayesian, so that's not even.
That's right. Aren't we all?
We all want to go to Taco Bell.
I love Taco Bell. Ever since they closed it over, I can't get it.
I think we need to get lunch. Right?
Well, let's thank our panelists. Great questions too, so thanks a lot.
Yeah, thank you.
So everybody follow us. We'll guide you to the food.